Lesson 2, Supporting Authentication and Authorization. All right, in the overview, again, supporting authentication and authorization. Check it out. We're doing multi-factor authentication. We're going to talk about things like workgroup versus domain versus home group. We'll be working with computer and user authentication, local accounts versus Microsoft accounts, workplace join, configure Windows Hello. All right, today's network admin, secure network resources accessed from the inside and outside of the organization. You see the computer network of today can extend beyond the physical location of the home, I was going to say the home PC, but you get the idea, from the home network. A well-designed authentication and authorization strategy is key to ensuring resource availability and integrity. The key pillars of information security. The biggies, I guess, are authentication and authorization. So authentication is that you're going to prove that you are you. Authorization is, well, what permissions do you have once you prove you are you? Confidentiality, are you authorized for that? Could be like a document. Maybe only HR is allowed to read it. Those kinds of things. Integrity, is data sent, the data received? Because if it isn't, then it's been tampered with. So we call that integrity. Non-repudiation. This means the data source is good, so we can make sure that it wasn't spoofed. Somebody isn't trying to trick you by offering a different data source. Multi-factor authentication. Well, authentication, let me give you a few examples. One is something you know, like a password or PIN number. Something you have could be a smart card. Something that is unique to you would be a biometric type thing, like maybe a retinal scanner for your eyes, or a fingerprint for your fingers, or you can even have a voice print. Did you know that using two of these is called a two-factor authentication? Here's a few authentication factors, such as the smart card reader. You know, you use those things every time you purchase something. You pop your smart card in there. A biometric reader, I'm looking at, looks like a fingerprint scanner there on the left-hand side. A PC where you're just typing in a password. So here's an example of a password. I'd say it's kind of a weak password myself. And then picture passwords, where we're actually going to get into that in the next couple slides there. So I'm going to hang on to that for a minute. Digital certificates is, you'll have those associated with documents and things, where you'll have a server that vouches for the authenticity of the documents that you're accessing. So those are called digital certificates. A strong password has the following characteristics. Contains at least 7 characters. Now in some other books I teach with, it'll say 8 characters. But for this book, 7 characters. Uses at least 1 character from the following: upper and lowercase letters, punctuation marks, numbers, does not include your logon name, your real name, or company name, does not include a complete word that can be found in the dictionary, should not be the same password that you have used in the past or used other website accounts. So here's some examples of weak passwords. I'd say the weakest password in the world is password. 1 2 3 4 5 6 7 8. That's a weak password. Jim Bob includes the names. John Doe includes not only the name, but look at this. This guy's given out his birth month and date and year of his birth. Can you believe that? Strong passwords on the right-hand side. I have special characters like the slashes. I have upper and lower case. I have numbers. Look at that. So this one has it all. The next one, I have special characters. I have upper and lower case. I have numbers. This one's a good one. The last one, look at this. They're kind of playing a little game with their name here. It says it's spelling a name, Treasure Hunter. But look, you're never going to find this in a dictionary because they're using special characters, upper and lower case, and numbers. So these are strong passwords. Pins and picture passwords. A PIN is a short numeric password used to authenticate a user to a system. A picture password is limited to 3 gestures. You can make circles, you can make straight lines, or taps. Here's the Windows screen where you set up a password, and the first thing you'll do is choose a password, and then you can choose the gestures that you're going to use on the password. So there's an example of that. Digital certificates, a collection of data that binds an identity to a key pair. And it uses something called a CA, or central authority, which happens to be a server. And in my little picture here, there's the server. And it is a computer that creates and manages the distribution of certificates. The most common digital certificate is X509. Now listen, there's a little bit to digital certificates. So I've got a 15-minute lecture that's going to tell you more than you'll ever want to know about digital certificates. So we're not going to test you as hard as, as in detail as what's going to be on this lecture. So let's check it out. It's about 15 minutes long. I'm just going to make it part of this lecture. So it's off of YouTube. There it is. I'll skip the commercial here. And commercial skip.
In this video from IT Free Training, I will look at what is a certificate. Certificates are used for security and identification, but how do they work? This video looks at what is a certificate and how they are used to secure communication and prove identity. First of all, what is a certificate? A certificate is simply a file or an electronic document that contains data fields. If you were to compare a digital certificate with a traditional physical certificate, you will notice some similarities. As shown in the traditional certificate, you can see who has issued the certificate. In this case, IT Free Training. If you had a certificate from an organization like a university, the certificate would have this printed on it so you know who issued it. An electronic certificate is issued from an authority as well. By looking at the data inside the certificate, it can easily be determined which authority it was issued from. The next question is, would you trust this authority? By doing a quick search on the internet, you may find many websites that will take your money and give you a certificate showing you have a PhD. An employer should not trust these certificates. If an employer was given a certificate that came from an educational institution like Harvard University, they would have good reason to trust this certificate. This is because in order for a person to obtain a certificate from Harvard University, they would have needed to complete all the necessary steps in order to achieve this. Electronic certificates work off the same principle of trust. Do you trust the person that issued the digital certificate like you would a physical certificate? If a certificate said that it was issued by Microsoft, would you trust this certificate? If a certificate came from a website that you had never heard of before, would you be so quick to trust it? As we will see later in the video, certificates use a trust model in order for the end user to know where the certificate has come from and whether it is genuine or not. The next point of interest is who the certificate was issued to. The certificate shown here was issued to John Doe. Like a physical certificate, an electronic certificate is issued to someone or something. For example, an electronic certificate could be issued to a user, computer, device, or web page. By using this information, the electronic certificate can be checked to see if the user, computer, device, or web page should be using that certificate. Just like a physical certificate, the name on the certificate can be checked to make sure that the person using it is the same person. If the name does not match, This means that someone is using a certificate they are not supposed to be, and thus the certificate is rejected. Some physical certificates have expiry dates. For example, certain IT certifications will expire after a certain date unless you pass additional exams. In this case, the example physical certificate has an expiry date. Electronic certificates also have an expiry date associated with them. Once this date is reached, the certificate can no longer be used. A common piece of data contained in an electronic certificate that is not contained in a physical certificate is the public key. The public key allows data to be encrypted that can only be decrypted using the private key. For example, if you had a certificate from Microsoft.com, you could use this certificate to encrypt data so that only people at Microsoft could decrypt it. The next part of the electronic certificate is the digital signature. This is like the wax seal on a physical certificate. Just like the wax seal, the digital signature proves the certificate came from a trusted source and is not a fake. The digital signature also provides an additional feature in that it provides a checksum-like function to the digital certificate. That is, it can be used to check if the certificate has been altered. This is only some of the data that is contained in a certificate. Other data also exists, like the algorithms and key sizes used. To understand how certificates work, it helps to have a closer look at the digital signature in the certificate. The first point to understand with a digital signature is the hash value. The hash value is a value that represents the certificate. The hash is calculated by putting the certificate through a mathematical function to produce a value. A simple hash function would be to add each byte in the file together to obtain a single number. Of course, the hash function used in certificates is more complex than this. The hash value is then put through a mathematical function using the private key to generate a digital signature. This digital signature is then added to the certificate. Now that the digital signature has been added to the certificate, it can be used later to check that the certificate has not been altered or damaged. To check the certificate, the digital signature is put through a mathematical function using the public key. The result of this should be the original hash value. If this value is not obtained, the person knows the certificate is corrupt or has been tampered with. The hash function is a one-way process, which means you cannot use the hash value to generate the original certificate. This essentially means that even though the private key is used in the process, it is not possible to use the digital signature to obtain the private key. So what exactly does the digital signature do? First, it provides a method for checking the identity. For example, if you had a certificate that was issued to itfreetraining.com, the name of the website could be included as a field in the certificate. When the certificate is downloaded to a client computer, the client computer checks the name on the certificate to see if it matches the website that they are trying to access. If it does, the certificate will be used. You can see that if another website also obtained this certificate and attempted to use it, the certificate would be rejected as the name in the certificate and website do not match. Remember that a certificate is essentially a file with data in it, so it is an easy process to change the name in the certificate. If this were to occur and an attempt was made to change the certificate, the digital signature would come into play. Notice that when a modified certificate is used, the digital signature will not match the data in the certificate, and the certificate will be rejected. This is how a certificate can be used to prove identity and how they protect themselves from being tampered with. The next question that arises is, if you were given a digital certificate, would you trust this certificate? Certificates work off a trust model. To illustrate this, consider an example that occurs often in the real world. In this example, let's say you have the company Microsoft. Microsoft makes operating systems, as we know, and you want to buy a laptop that will work with Windows 8. In order to do this, you find a laptop and see that the laptop has a sticker on it saying Windows 8 compatible. Even though the laptop is not made by Microsoft, you can be assured that because it has this sticker, Windows 8 will work on this laptop. So what has happened here? You are trusting that the manufacturer of the laptop has put the sticker on the laptop because their laptop works with Windows 8. You are trusting Microsoft that they would not allow a sticker like this to be put on a laptop that would not run Windows 8. Thus, you can see how one trusts the other, and the person who purchases the laptop must trust both. So how does this all relate to certificates? Certificates use the same type of trust model. At the top, you have a certificate authority. In this example, I will use the certificate authority VeriSign. VeriSign has been around a long time and is well trusted on the Internet. A certificate authority's job is to issue certificates. These certificates can be used for users, computers, devices, and web pages. Let's say IT Free Training wants to get a certificate for their web page. To do this, they obtain a certificate from VeriSign, which would allow a visitor to the IT Free Training website to use encryption like SSL. Before VeriSign could issue a certificate to IT Free Training, a number of checks are performed. These checks include checking who registered the domain name and a number of checks on the business. This helps prevent certificates being issued to individuals who want to use the certificates for illegal activities. For example, if someone attempted to obtain a certificate for Microsoft.com, notice that the I has been changed to a 1, this would be denied. What this essentially means is that if you use a certificate from VeriSign, you can be assured that a number of checks have been performed before the certificate was issued. It is possible for a certificate to be issued to a company that is doing the wrong thing, but at least you can be assured that some checks have been performed to determine that they are a valid company. The next question is, what happens when a user connects to the IT Free Training website and obtains the certificate? How does it know it is valid and from VeriSign? And why would it trust and thus use this certificate? By default, a number of certificates are installed on the client computer when the operating system is installed. These include a VeriSign certificate. Since the certificate is installed locally in the OS will trust any certificates issued from VeriSign. When the certificate is downloaded from IT Free Training, the digital signature is used in the certificate to determine a number of different things. First, that the certificate has not been tampered with, and the website matches the website in the certificate. Using the local certificate installed in the OS, Windows can check the certificate obtained from IT Free Training to see if it is, in fact, a VeriSign certificate. You can start to see how the certificate trust model works. The computer must trust the certificate authority that the certificate came from, just like you would trust an organization like Harvard University. If you were given a certificate with the Harvard University logo on it, would you trust it? Also consider that if you were an employer that had never heard of Harvard University, would you trust a certificate from an educational institution that you had never heard of before? Certificates work the same way. You need to trust who issued the certificate in order to start using it. When you are surfing on the Internet, you may be presented with the following screen. This is essentially telling you that you visited a website that Windows does not trust. This essentially means no certificate is installed locally on the computer, or the site has not been placed in an exception list. What this essentially means from a user's perspective is that Windows has not been configured to trust certificates from this source. In this case, the user can take the risk and accept the certificate and hope for the best, or not to open the website. Although certificate authorities like VeriSign are trusted by Windows by default, you may want to use your own certificate authority. Besides having complete control over the certificate authority, certificates from companies like VeriSign do cost money. If you have your own certificate authority, you can issue as many certificates as you wish at no cost besides the cost for the operating system and hardware to run it on. When deploying a certificate infrastructure, This will often be done at a number of different levels. At the top you have the root CA. The root CA will issue certificates to the subordinate or second level certificate authorities. Often what will happen after the root CA has issued certificates to the second level authorities, the root CA will be taken offline. Since the root CA holds the private key that effectively is the key to the entire certification infrastructure, this should be protected. In some cases, a company will install the root CA on removable media. Once the root CA is not needed anymore, the removable media is placed in a safe until it is needed again. The second level CAs are free to issue certificates without the root CA, so the system will work fine even though the root CA is offline. Having the root CA offline helps keep it secure. The second level CA will often issue certificates to users in computers. For example, a certificate may be issued to a user so their identity can be checked when using a VPN connection. It is also possible to have additional levels of certificate authorities if your organization requires it. In this example, let us consider what happens when a computer attempts to connect to a web server. The certificate for that website will be downloaded to the client. But will the client trust that certificate? In order for the certificate to automatically be trusted, a certificate from the root CA needs to be installed locally on the client computer. Once this certificate is installed on the computer will trust any certificate automatically that comes from any certificate authority in this hierarchy. It is kind of like the old saying, any friend of yours is a friend of mine. If the root CA is trusted by the client, any of the child CAs will be trusted automatically. I hope this video has given you a good understanding of how certificates can check identity.
Okay, as far as the part in the book that talks about digital certificates, I think you learned a lot more than necessary, but I thought it was a great explanation of how digital certificates work. If you want to view the certification path, basically, I have an example right here. Here's one from Contoso. So this gives you the certification path of a digital certificate to make sure it was issued by a trusted certificate authority. Now this kind of stuff, I don't know if you'd see on help desk, but a technician would be aware of these types of things. On a local computer running Windows, the certificates are stored in a certificate store. Notice it's called physical store name right there. There's the certificates. Okay, so from Windows 10 or Microsoft Server, you can access the certificate store with the certificate snap-in, where you hit the start button, you get your MMC, and then add the certificate's MMC snap-on. Supporting smart cards and virtual smart cards is the first question: what a user owns or possesses. That was a smart card. We saw that on an earlier slide. So you've used these smart cards before. They have a chip in them. They may be associated with a PIN, a digital signature. We just saw that in the video. So a digital signature is where you have kind of like somebody that vouches that the certificates or CAs or components to create, distribute, validate, revoke, all those are good sources. And then VSCs emulate a smart card but require a TPM chip, and you'll find a TPM chip inside your computer. So if you want VSCs to work, which stands for Virtual Smart Card, you're also going to need a chip to be able to read that. All right, supporting Windows Hello and Microsoft Passport. Biometrics takes advantage of the uniqueness of every individual, and the user has to physically be present for the identification. Examples are fingerprint, facial recognition, voice, or eye. So it's reading the retinal print in your eye. Windows Hello is a Windows 10 biometric authentication system to unlock devices. So if you want to use that, basically if you just had like a camera built into your laptop with Windows 10, you could use facial recognition or a microphone for voice. Microsoft Passport is a two-factor authentication that consists of an enrolled device, such as a smartphone, and a Windows Hello biometric or PIN. Supporting local domain and Microsoft accounts. Employees log on to user accounts and gain access to network resources. So here's a few types of accounts. Local. The local user, limited to that computer. So, if you had a standalone computer, you'd log in as the local user. Domain-based. Provides an access to designated resources on that domain. So maybe files, folders, printers, any resource that would be on the domain-based network. Microsoft User enables you to synchronize your desktop across multiple Windows 10 devices. I mean, you could have a Windows 10 device that's as small as a smartphone. And so basically you can synchronize your desktop across all these different devices. Microsoft account kind of looks like this. So in Windows 10 settings, you can change the account type. So here's admin. You can set up for, like for me at home, I might have some separate ones set up for my kids. Managing users with computer management. So you can access this from search, computer management to manage your users. So this would be like in Windows 10, you could run this computer management snap-on or snap-in. You can also create a new domain user from Active Directory users and computers. So here's users. I right-click on that. I select New Object User, and guess what? I can enter all the stuff in from here. Let's see what the difference between a work group and a domain is. In a work group, it's a peer-to-peer environment. So everybody is keeping their own passwords, their own user logins and things like that. So if you look real close to the logons, you can see that they are unique to each individual computer. So every computer handles its own resources and accounts. That's called distributed authentication. Now let's look at the domain. So domain is client-server based, which means you're going to have one domain controller that's going to handle the resources and accounts for everybody. That's called central authentication. Notice that just like here at Stark State, you would type in Stark State / and then your username, which here at the campus is like first initial, last name, birth, month, and day. Your password would be your, your three initials, a dot, and the first 6 of your social security numbers. So you wouldn't have that on each individual device, but you would have a domain controller that controls the logins for everybody. Authentication terms. A user account is used by Windows to determine what changes you can make on the computer, to determine which files and folders you have access to, and to track personal preferences. Computer accounts provide a means for authenticating and auditing the computer's access to a Windows network and its access to domain resources. So you have user accounts, you have computer accounts. Kerberos and NTLM authentication. So when a user logs into a computer, the user logs on using Kerberos or the NTLM protocol. Kerberos is preferred because it's always secure, but it's not always available. So if you have like an older Windows NT system, like before the year 2000, not like there's too many of those running around, you would have an NTLM protocol for that. So Kerberos is really the main one that we use today. Here's the Kerberos authentication process, and here's a little video to explain Kerberos.
How Kerberos works. Hi, I'm Don Jones, and as you probably know, Kerberos is the native authentication protocol in Active Directory, so it's used by Windows networks everywhere, but it's surprising how few people really know how the protocol works. And if you're going to understand some of Active Directory's more advanced concepts like delegation and so forth, it's important to understand what's going on under the hood in Kerberos. So let's dive in. So in any authentication situation, you really have three different parties that are involved. The first is the client. Now, sometimes that's a client computer, but more frequently it's an actual user who's sitting at that computer and trying to access resources. Then there's the resource that they're trying to access. In this example, it'll be some files on a file server. And there's the KDC, the Key Distribution Center. Now, in an Active Directory network, that's an Active Directory domain controller. And this is the guy that really kind of brings everybody together. Interestingly, in Kerberos, there's no communication between the resource and the KDC. There doesn't need to be. The client actually takes on the majority of the processing burden in Kerberos, which kind of distributes that authentication workload across the network. But it does so in a way that's secure and trustworthy, as we're going to see. So things kick off when the client attempts to actually log on to the network. Here's how that works. The client constructs an authenticator. Now that's a special little package that says, here's who I claim to be, and some other information, including the date and the time. Now, those authenticators are only good for a certain period of time. That way they can't be captured and then replayed back on the network by an attacker. So this will represent that authenticator. Now, a portion of that is unencrypted, the user's name and so forth. That way, when this gets sent off, the KDC or domain controller can see who's trying to authenticate. But a portion of it is encrypted using the user's password. So that's what this pink key will represent, and that's what this pink lock will represent, that the user's password, which is known to the user, has been used as an encryption key. This is an important concept because it emphasizes the fact that Kerberos doesn't transmit your password across the network. It uses it as a shared secret. Now, shared secret simply means that when this thing is sent off to the domain controller can open it up and it can see in clear text, okay, this is who that user claims to be. I'm going to go in my database and look up what I think their password is and see if I can use it to decrypt the authenticator. If I can't, well, then this was clearly encrypted with a password other than the one I know about, so this user isn't who they say they are. If I can decrypt it, though, then this user must be who they say they are because they've got the correct password. So from this point, I don't need that authenticator anymore. It can actually just completely go away. Instead, I'm going to create a ticket granting ticket, or a TGT. Now, I, as the domain controller, have my own encryption key that I'm going to use to encrypt a portion of this TGT. Now, I've already gone through the laborious process of looking up this user and making sure they are who they say they are. So I'm going to save all that information in here, but I'm going to encrypt it using a key that only I know. Then I'm going to transmit this whole thing back to the client, and they're going to store it in a special area of memory called the Kerberos tray. Now that's an area of memory that cannot be swapped out to disk. It always lives in memory. That way if the computer crashes, this information hasn't been saved anywhere persistent. Okay, so now the client is logged on, they're ready to go, and they're ready to get to something on a file server. So my computer looks at my Kerberos tray and says, well, you don't have a ticket for the file server. So we're going to go back to the Key Distribution Center, and what we're going to do is send it this ticket granting ticket along with a request. Hey, I need a ticket for the file server. The Key Distribution Center, the domain controller, does not have to look up my information again. It simply uses its key to decrypt the TGT that it gave me earlier. If it decrypts successfully, then it knows that this is the information it generated itself previously. Now, these ticket granting tickets are usually good for 8 hours by default, so periodically they will have to be destroyed and renewed. That way the domain controller gets an opportunity to revalidate my identity, but it doesn't have to do that every time, which saves it some effort. So the client actually does keep a copy of this in its Kerberos tray. It sent a copy off to the domain controller. The domain controller knows who I am now and can thus generate a ticket. Now here's the cool thing. Because this file server is also a domain member, the domain controller has its logon password, which it uses to encrypt this ticket. Now, there's no communication to the file server itself. Instead, this ticket is created by the domain controller and given to the client, who stores it in the Kerberos tray. Now, for the next 8 hours, while that ticket is still good, anytime the client needs to access something on that file server, all it has to do is create a copy of that ticket and send it to the file server. The file server says, I have no idea who you are. I've never seen you before, so I'm going to use my password, which I know, to try and decrypt this ticket. If I'm able to do so, then this ticket must have been generated by the KDC, because that's the only other person that knows my password. That tells me, the file server, that this is a legitimate ticket. So I'm going to go ahead and accept that. I'll open it up. That'll tell me your username and what groups you're a member of, and I'll use that information to decide what you're allowed to access. And every time you come back to me, Mr. Client, you're going to need to resend me a copy of this certificate. That way I, the file server, don't have to store all this garbage in memory. Because the file server is working with hundreds, potentially thousands of users. If it had to keep all those tickets, it would be a huge pain in the neck. So there's actually a command line utility you can get, or a Windows utility called KerbTray. It's in the resource kit. It's available for download on the internet, and it lets you view this Kerberos tray so you can see all of the tickets that a client has gathered. So this is how authentication works. The client goes to the KDC to get the ticket, and then it stores them and presents them to a file server. And that's how the whole Kerberos protocol really works. I hope this has been informative for you, and I'd like to thank you for viewing.
All right, so there you go. That should explain the Kerberos process pretty well, and we'll go to the next slide. Securing channels with TLS and SSL. TLS, Transport Layer Security. SSL, Secure Sockets Layer. These are communication protocols that can securely authenticate servers and clients. They can protect you from eavesdropping and tampering. Windows implements TLS and SSL through the S-Channel Security Support Provider. So this is an example of a client and a server, and they have something called a handshake process where SSL is used to send hello, cipher suite, and client random to the SSL server. The server responds back by sending the server random and SSL certification or a private key. Then the client server sends the pre-master key generated using the public key, and the SSL server, the client server also sends the pre-master key decrypted using the private key. The master key or master secret is now in place, and the master key is used for encryption and decryption. So this is just an example of how we secure our channels between the client server and the SSL server. Client is like your PC or your laptop. So it's a very secure method to be able to communicate. Access tokens and credential caching. So when a user is authenticated, the LSA or local security authority creates a primary access token for the user. Now a token is just used to get access to something. It could be documents or whatever. But an access token contains a SID, which is a security identifier so they can find you in the system, and all the SIDs for the groups to which the user belongs and the user's privileges. So it identifies you and what you can do when you're in the system. Windows submits the access token on behalf of the user. So there's a token access example. Credential Manager allows you to store credentials that you use to log into websites or other computers on the network. Windows automatically logs you onto websites and other computers, and credentials are saved in special folders on your computer called vaults. So from Control Panel, User Accounts, you can access the Credential Manager. Here's some examples right there. Using account policies. Group policy is one of the most powerful features of Active Directory that controls user accounts and computer accounts. And group policy provides the centralized management and configuration of operating systems, apps, and user settings in an Active Directory environment. The account policies contain three subsets, like the password policy, which determines your password settings, how long a password's good for, things like that. Account lockout policies. So like if somebody types in the password incorrectly like 5 times, how long would you get locked out? And the Kerberos policy determines how the ticket determines ticket lifetimes and enforcement. So I think you heard somewhere in one of those videos that a ticket would be maybe good for 8 hours. So that's something we would talk more about if you're in my computer networking classes. Password policy note of a group policy. You set the minimum length, and I think we said that a good password's at least 7 characters, so you'd probably set it for that. They have to meet complexity requirements, such as upper and lower case special characters. Maximum password age. I think around here at Stark State we might have that set up for like 90 days. Enforced password history. So you couldn't use a password and then change it to another password and then go back to the first password someday. And then a minimum password age. So all of these would be password policies. An example of a new password settings container kind of look like this. And then everything we just talked about right here is checked off that you can use and adjust the settings. An example of the account lockout settings. Here's the account lockout duration, where maybe you're locked off for 15 minutes or whatever. So the threshold, how many attempts, etc. So those are examples of those lockout settings. And then home group is a group of computers on a home network. So if you have like Windows 10 Home, you can share your files and printers and things like that with home group. To protect your home group, you can use a password. And home groups are relatively limited because you can only share the contents of the libraries and the user's profile. Home group is available starting with Windows 7, so Windows 10 would work just fine. And that's it.